Welcome to the third video in my series on proving the twin primes conjecture. In the last video we learned about motif tables, such as the one you see here on the screen. In this video we extend the motif table concept from partial twin primes to actual twin primes. Since 19 is the eighth prime, we say that q sub 8 equals 19 and that q squared sub 8 equals 361. And because 361 is found on row 60 of the motif table, we say that capital K sub 8 equals 60. Definition 20. The sequence capital K sub m is the sequence of j's, that is row numbers, of the motif table for the rows that contain prime squares. In other words, q squared sub m. We will find that prime squares are always beta complements and therefore are always on a row of the motif table, as this theorem demonstrates. Theorem 1d. Prime squares and multiples of 6. The square of any prime number larger than 4 is a multiple of 6 plus 1. In other words, a beta complement. Proof. Let h, a member of the set of natural numbers greater than 0, be arbitrary. According to Theorem 1b, primes and multiples of 6, any prime q larger than 4 equals either 6h minus 1 or 6h plus 1. The square of q then will fit one of two cases. Case 1, q equals 6h minus 1. Then q squared equals 6h minus 1 times 6h minus 1 equals 36h squared minus 12h plus 1. Since 36h squared minus 12h is a multiple of 6 for all h, the expression resolves to a multiple of 6 plus 1. Case 2, q equals 6h plus 1. This expression too resolves to a multiple of 6 plus 1. Thus the square of any prime number larger than 4 is a multiple of 6 plus 1 as required. Let's calculate the twin primes count up to and including q squared sub 8 equals 361 using the CAP approximations method. To calculate the count, we begin with equation 2d from theorem 2f partial twins formula and modify it as follows. First, we substitute k sub m for j since they are equivalent in this context. We then change the numerator so that it subtracts a variable designated as lambda, the blockage setting, also called the lag setting, instead of subtracting 2. Finally, we add a floor function. The partial twins calc will always result in an integer for equalized factor channels, but the approximation calc will yield a fraction. So we round the approximation result down to the nearest integer with the floor function. Our modified equation then is equation 2f. Var theta sub m equals k sub m times q sub 3 minus lambda the quantity over q sub 3 times up through times q sub m minus lambda the quantity over q sub m, rounded down to the nearest integer, where q sub m is the basal prime whose square is found on row k sub m of the table. Thus the approximations calc for the twin primes count up to the square of 19, that is for var theta sub 8, is the one we see here. Definition 18b. The blockage setting, represented with lambda, a member of the set of real numbers greater than or equal to 2, is the amount subtracted from the factors in the numerators of the elements in equation 2f. The blockage setting reflects the blockages per motif for a given factor. Now we learned in Theorem 2f partial twins formula that when motifs are equalized at the bottom, setting lambda to 2 will give a perfect count of the partial twins for the equalized factor channels. Unfortunately, the situation is not so simple when the factor channels are not equalized as in this table. The main point is that we calculate the twin prime counts at each prime square because that is the point at which we must increment m and add a new term to equation 2f. We can use equation 2f with a constant blockage setting, lambda, to produce a lower bound. Here is an example of such a lower bound. As you can see, the lower bound is always slightly lower than the actuals. And of course we can always lower the bound by increasing the blockage setting. The blockage setting used is constant and slightly larger than 2. It's 2.065 in fact. For the partial twins calculations, we used a blockage setting of 2. As we saw, it produces 100% accurate results. Unfortunately, it isn't possible to equalize all of the factor channels when we calculate the number of twins up to a given prime square. The lowest row on which the factor channels will equalize is always the product of the factors. We saw, for example, that for factors 5, 7, 11, and 13, we needed 5005 k-rows to equalize all 4 of them. The problem is that the beta complement at j equals 5005 is 30,031, which has 38 factor channels not counting 2 and 3, as can be seen in this motif table. You can see the 4 equalized factor channels at the lower left of the motif table, but consider the 34 channels that come after. The areas that are not enclosed within red boxes are incomplete motifs. The reason we can't use a lambda setting of 2 is that these incomplete motifs have extra blockages. The formula, however, is for complete motifs. Thus, if we subtract 2 from the factor values in the numerators of the fractions that are used, those fractions will be too large. The result will be an overcalculation of the twins' count. What this means is that use of a constant lambda is better suited to calculating a lower bound than it is to calculating an approximation. To calculate an approximation, we must use a floating lambda, that is, a different lambda setting for each fraction used to calculate the product. Now we look at the combinatoric approximation, or CAP, presented in the first video in this series. The sequence of row numbers, k sub m, of the motif table rows that contain each basal prime square plays an important role in the calculation of the prime twin counts. Indeed, the sequence constitutes one of the 2 pillars of the calculation. Lemma 3a, the infinitude of k. The sequence k sub m diverges to infinity as m tends to infinity. Proof: the sequence k sub m is a sequence of j's, that is, motif table row numbers for the rows that contain prime squares, that is, q squared sub m. The sequence can be rewritten in terms of the prime squares as equation 3b, k sub m equals q squared sub m minus 1, the quantity, over 6. The sequence q sub m is simply the sequence of prime numbers, which of course diverges to infinity, and since q sub m diverges to infinity, then so does q squared sub m. It follows then from equation 3b that k sub m diverges to infinity as well, as required. Note that the convention is to represent sequences within parentheses. K sub m is an individual case of k at index m. But k sub m within parentheses is the entire sequence of such cases. If the lambda used is constant, the fraction that we multiply times k for the var theta calculation is designated as h. But if the lambda value is floated, the fraction is designated as h hat. For the cap, we use a floated lambda, so the formula is the one shown here. Equation 3i, h hat sub m equals the product from g equals 3 to m of q sub g minus lambda sub g, the quantity, over q sub g. Thus we calculate the var theta sequence for the cap as follows. Equation 3g, var theta sub m equals k sub m times h hat sub m rounded down to the nearest integer. The actual's analog to var theta is designated as theta. Definition 19. The sequence theta sub m is the sequence of actual twins counts in which each theta sub m value is the twins count up to the square of the basal prime q sub m. The actual's analog to h hat is called I. Definition 20b. The sequence I sub m is a sequence of fractions which multiply k sub m to yield theta sub m. Because theta consists of actual counts, it's not calculated with a formula. Each I value is calculated from theta with the formula Equation 3e. I sub m equals theta sub m over k sub m. The sequence k is the first pillar in understanding the prime twin counts, and the I sequence is the second. Definition 21. An inverse logarithmic sequence is a sequence of the form 1 over the log of n, the quantity, raised to the x power, where n is a member of the set of natural numbers greater than 1, and x is a member of the set of real numbers greater than 0. Lemma 3b. The character of I. The sequence I is an inverse logarithmic null sequence. Proof. The sequence I sub m can be closely approximated by another sequence, v sub m, which is generated using the formula equation 3f. v sub m equals 1 over the log of m, the quantity, raised to the c power, where c is a constant, 1.85377, and m, a member of the set of natural numbers greater than 2, is the index of the q sub m sequence. Here is a plot of I sub m against m with the L shape that's characteristic of inverse logarithmic sequences. The red plot is for v, generated using equation 3f, but with a c value of 1. Both plots have similar shapes, but v with an exponent of 1 is much higher than I. That is, it approaches 0 more slowly. Here we see the plot of v with a c value of 1.85377. The effect of raising the v sequence to that power is to move the sequence down and to align it with I. Here is a super-zoomed close-up of the two graphs. Thus, when v is raised to this power, the two sequences are virtually identical. At the same time, we can see from equation 3f that the approximation sequence v fits the definition of an inverse logarithmic sequence, since it uses the inverse of the log of m. But if v qualifies as an inverse logarithmic sequence, then so does I, in view of the two sequences' remarkable similarity. Likewise, it should be clear from equation 3f that the v sequence approaches 0 as m tends to infinity. V therefore constitutes a null sequence. But if v qualifies as a null sequence, then I likewise qualifies as a null sequence. Thus I is an inverse logarithmic null sequence, as required. We calculate the approximation with the following formulas. As a practical matter, we can calculate the result for equation 3i from the previous h hat value using equation 3j. At each prime square, we must increment m and calculate a new h hat value, with q sub m added to the formula as a new principal factor. This is because, as we learned in Theorem 1e, each principal factor becomes operative at its square. We denote a floated blockage setting with lambda sub m, in which the subscript indicates that each instance has its own value. Working from this simpler equation, we can incorporate v sub m into the approximation by simply setting the amount by which we adjust the previous h hat value, as shown in equation 3k, and then solving for lambda. The result is equation 3m. You will notice in this table that the values in the last column and the third column are identical, but the third column is simply v sub m. This formula for lambda sub m, then, calculates blockage settings that ensure h hat equals v. Now the actual blockages decrease because as the principal factors grow larger, the extra blockages from incomplete motifs have less and less significance. Hence the result is to approximate I very precisely, and thereby create an extremely accurate approximation to the actual twins distribution. In the next video, we craft two proofs for the twin primes conjecture using real analysis. If you care about mathematics and care about the twin primes conjecture, you won't want to miss it. I'll see you there. Be sure to subscribe and press the bell so you will be notified when the next video in the series becomes available.